All right, so next we're moving to discussing the idea of spread. So we wouldn't even have statistics if we didn't have variability or variation in our data. People, measurements, even repeated measurements, just everything out there varies, right? If you ever get, you get up and you go weigh yourself on your scale at home, and you get on it once and it says something, and you get off and you get it back on it again, and it might be just a little bit different. That's why when you take physics or chemistry class, they make you weigh your stuff several times and then use the average of those weights, because there's variability even in measurements of the same thing. So, and of course people measure, vary and whatnot. So we want to get an idea of how much variation there is in our data. And so to that end, we need to come up with a statistic that measures that. So of course here, why do we care about variability in the first place? Well, a lot of times we want consistency in our sample or our population. We want to have low variability. And usually we'll want this in manufactured goods. We do want, all the TVs of a certain type, they should all be performing the same, right? All cars of a certain make and model, they should all be performing the same. We really want all your apples at the store to be, of the same type, to be similar, right? We don't want a whole lot of variability in those sorts of things. So more consistency means the same thing as less variability. Okay. And so we want to be able to know how much variability we have in our data. So we'll go back to our example. We're looking for a house at about $250,000. And so we've got neighborhood A, where all of the houses fall in about 225 to 275 range. So they're all pretty consistent, right? So here, we've got our house and our house and our house, and they're all right around the same, right? And so the variability of the average price is $250, and all the houses are right around there, which is typically what you want in a neighborhood, because that helps to maintain the value of the houses. Now, in neighborhood B, it also has an average value of $250,000. But unlike our first neighborhood, we've got $30,000 abandoned falling down houses right next door to $800,000 McMansions, right? You know that there's places in Atlanta like that. So this data is way more spread out, but the mean is still there in the middle at about 250. Right here we've got the mean at about 250. And in our neighborhood B, we've got the same mean, but our data is way more spread out. Not that there's a whole lot of different values, but that it's much more spread out from the mean. The data values are further away from the mean on average. And that's what we need to be concerned about, right? That sort of neighborhood, either people are going to go in and buy all the abandoned houses and turn them into McMansions, which might be a good thing, or whatever caused the abandoned houses to be abandoned is going to cause the McMansions to go downhill too and bring the whole neighborhood down. Very rare that it's going to stay in that kind of in-between state. So this is just an made-up example between a very consistent neighborhood and a neighborhood that has prices that are very spread out. Okay, so our measures of spread. First off, easiest, rarely used, we have the range. This is your maximum value minus your minimum value. This one is not resistant at all, because as soon as that highest or lowest data value changes, your range has changed by however much it changed. So if you have skewness, your range all of a sudden has gotten much bigger, or if you've got an outlier, you might have all your data all right here all together, and then you've got that one outlier, and the range is going to be huge on this thing, but the vast majority of your data is very consistent. That's not representative of the data. So a little bit better is standard deviation. Standard deviation, the statistic standard deviation, we use S. And if we're talking about a population, and we want to talk about the standard deviation, we're going to use a Greek letter called sigma, lowercase sigma. All right. So this one, we are going to let the computer, let GeoGebra and Minitab calculate. This is not fun to calculate by hand. You can see the formula looks a little scary. You're not going to calculate it by hand. All right. We generally pair the standard deviation with mean. It has a similar level of resistance. So we'll just write that, similar level of resistance, which means, if you've got some outliers or skewness, that's going to impact the standard deviation some, but not nearly as much as the range. All right. So it gives a measure of the overall variation in the data set. And the way I like to think about it is it's essentially the average distance of the data points from the mean. So I like to think of everybody living on, a street all together. And, there's whatever distance is between everybody's houses. This is a really long street. And how many did I do here? 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, so I got 9. So let's say, roughly speaking, Kathy's here sitting in the middle. And Leilani is next door, and Jermaine is next door, and Shanika, and whoever else. Let's see who else is in here. Precious, Jenny, and so on. All right. I'm doing good to remember y'all's names that much at this, since we've only had 2 classes, right? So Kathy here, she's the mean in our data set, let's say. All right. So she's going to have this big party to celebrate Memorial Day, right? And so the question is, well, how far does everybody in the class have to walk to get to Kathy's house? So, and of course, Leilani, she's got to walk 1 unit over, right? And Jermaine, he's got to walk, let's say, 2 units, and Jenny's got to walk 3, and so on. So that is basically this x minus x bar. How far are you from the mean? Now, the problem is Shanika, she lives on the other side of Kathy, so her distance is also 1, but it's the other direction, right? When we do her position minus Kathy's, we're going to get a negative number. So because of that, we really want to make it positive, so we're going to square all of those distances. So Precious, she lives like 2 units away, and whoever's next to her is 3, and so on and so forth. So we're going to add up all of those distances and get whatever that sum is. And then this is why it's not an average. Instead of dividing by the total number, because Kathy, she lives at her house, she's traveling a distance of 0. There's, how many did I say? I said 10? No, 9. 1, 2, 3, 4. Yeah, there's 9 data values in here. So if it was a mean, we'd divide by 9. We're only going to divide by 8, n minus 1. All right. Now, if we stop here, this is the variance. I don't like it very much, which we use either S squared for statistics or sigma squared. And then to get the standard deviation, we just take the square root. Okay. So like I said, we're going to let Minitab and GeoGebra do that. So just a quick standard deviation example. You have some test scores here, very, very quick. And I set this up so that the mean's easily found. It's 85. So usually it is easiest to go kind of like a table. So we would have for our 79, x minus x bar, 79 minus 85, that is -6. We square it, we'll get 36. For data value 85, 85 minus the mean is 0. Square it, we get 0. 91, we would get 91 minus 85, that is 6. Square it, we get 36. So then we're going to add all of those up. So summation x minus x bar squared, 36 plus 0 plus 36, that is 72. And therefore our variance is going to be the summation over n minus 1, so 3 minus 1, which is 2. So 72 over 2, which is 36. So our variance is 36. Standard deviation is just the square root of that. So square root of 36, 6. So, this one's easy because there's only 3 data values. You don't want to do this by hand for anything bigger. It's a pain in the rear. All right, so this one we're going to put in. This will be the last example, I guess, for this one. Actually, you know what? Let me stop and we'll break the examples out into another short video.